Good morning, Geodesy lover. We're going to talk about coordinate systems, and there is a number of things, very interesting things for us to discuss. And so here you go. Um, Here's the sequence of topics for us to discuss. Basically, definitions, celestial sphere. And then we have a number of coordinate systems. Let me go and get a color here. I have no one to choose the color for me. Pointer options. Now I want the arrow. I want the how does it work here? Come on. Ink color. Okay, I'm gonna get red. And so all that are coordinate systems. Okay, we're going to look at all of them. Here's another one. So actually starts from here. Every system, and system here I refer to coordinate system. These are coordinate systems used in Geodesy. And for several different reasons. They all exist. And they have an explanation, justification why they exist. If you think from a practical perspective, in the kind of a professional practice, if we're going to use mostly the conventional terrestrial system, the orbital system, and okay, I have to talk here about the local astronomical system, and that is the geodetic coordinate system. Okay, these are the ones that we use the most. Now, in all these topics here, there is one that is very, very important. It's relatively recent. It deals with time variations of coordinates. And this is very important, and I'm going to have a full section just dedicated for that. I forgot to count the time here. So before we talk about this, let me just explain to you how dimensionality has evolved in geodesy, because here it's easy for us to think about four-dimensional geodesy, which is basically say four components x, y, z plus time. Or you can think of a phi, lambda, and h, latitude, longitude, height, and time. But it wasn't like that. Okay, we traditionally geodesy was 1D and 2D totally different. So we had the vertical positioning that was basically just the height of a point above a reference. Okay, so this is just one dimension. Or you'd have the and that's what would be leveling, basically what we'd call the geodetic leveling. That would be the highest precision that we can get. But there was also the horizontal positioning by itself that would be done independently. And here we're talking about just two components, lat and long. And that was done usually related to a curved or plane surface. A curved surface would be basically a reference ellipsoid that would be chosen, and a plane surface could be a mapping plane. In the beginning, these two-dimensional horizontal position would be just astronomical positioning, and then techniques evolved. The increasing use of theodolites allowed for triangulation, and then came the tellurimeter after the World War, and then we had basically traverses, geodetic traverses. So, but the bottom line is that the vertical positioning and horizontal positioning, they were independent. They could be merged at times in what we call 2D plus 1D. We are still talking about this is not a full 3D, it's 2D plus 1D, because we had horizontal networks and vertical networks. Horizontal and vertical positioning done independently, but they could cover same points, or they follow about the same region, and that was basically these big geodetic networks that we have, for example, in Canada, which were based for the NAD27, and it served also for NAD83. They both datums had, in the case of NAD, they still have lots of information that comes from classical horizontal plus vertical positioning. Now, well, actually, I should say that the NAD is more a horizontal thing, and the vertical is more the Canadian vertical system. But nevertheless, the networks they have been developed together. So the other thing that people start to do early in the last century was to start looking for monitoring deformations, crucial deformations. And what they do, they would be doing installing horizontal networks and vertical networks in places, and they would do that at particular time epochs. Say they will go in California or in Vancouver Island and do a survey in 1930, and then they would go back and resurvey the whole thing in 1940, and I use the word surveying here in the sense of collecting data. These would be the highest accuracy possible, so it would be in the realm of geodesy, and then they'll go back in 1950, and then these are the 3 time tags. So time is just a tag in the sense that it happens. These are episodic, excuse me, events. Now, then comes space geodesy, extraterrestrial positioning, when it became possible to get 3D positioning directly. And 3D positioning, as we're going to see, we talk about basically having position in a Cartesian coordinate system. So X, Y, Z, these are not coordinates on a mapping plane. These are actual 3D coordinates in space, and in a Cartesian space. And of course, we can relate X, Y, Z. We can transform to latitude, longitude, and height. These are not the same things. We're going to see and emphasize X is not the latitude, Y is not longitude, Z is not height. Okay, they are in different. This is a Cartesian coordinate system. X, Y, Z, and phi lambda H is a curvilinear coordinate system. And but in the beginning, people were using space geodesy, doing again surveys, collecting data in episodic times. Now these could be, say, even intervals of days, but it was not continuous. Lately, with full-blown constellations of GPS, now Galileo, or sorry, GLONASS. Galileo is not a full constellation yet. GLONASS, GPS and GLONASS. We have the permanent stations. Okay, the stations that collect data all the time, and then indeed we have what we call the 4-dimensional geodesy, where time is a variable. Okay, so 6 minutes in this interesting discussion. I just want to emphasize what I mentioned about the NAD 83 and 27. They are not, this is just an example, they are example of horizontal datum, okay, and but we can, I mean, the networks would cross in certain points. The horizontal and vertical networks are independent. Okay, something very important when we talk about coordinate system. This is very basic, but I think it's important to say again that a coordinate system, you need a few things, otherwise it's not a coordinate system. One thing is the location of an origin. Okay, we have to have a point that will have basically 0, 0. Okay, and then the orientation of this axis. So I'm just drawing here a two-dimensional coordinate system, a horizontal coordinate system, and let's suppose that one of the axes will point towards the North Pole, okay, and the other one is usually orthogonal. So we can think then that we have here growing of latitude and growing of longitude. We have to define relationship how plane coordinates relate to curvilinear surface, and that's for us is important because we basically use we do positioning in many instances on the Earth or near the Earth, and we use curvilinear surface, which is basically the ellipsoid reference parameters that define the position of a point within the coordinate system. And again, this is an interrelationship between the Cartesian coordinate system and the surface that we want to represent the points. And something that is very important and often overlooked is the unit of measure along the coordinates, the axis, okay, because it's not just a question of defining, oh, they were working with metric system, but it's defining that indeed the basic unit would be meter, okay, and this is important, particularly when we connect, first of all, when we determine positions on this coordinate system, and we have measurements, and if you measure, say, distances with the EDM that is not well calibrated, we may have a distance between 2 points that may be off by 1 millimeter systematically. So actually these measures that we have along the along the axis, they are not going to be meter, they are going to be actually say 0.999 meters instead of a meter. Well, that's this is the problem of scale. Okay, now when you talk about coordinate systems, and this figure that you see is very useful. I love this figure, and I hope that you can appreciate that, because it describes the whole thing we're going to talk about. So let's start from the left hand side, the so-called heliocentric systems. Okay, they actually are celestial coordinate systems. So everything that is in this oval are celestial coordinate systems. So they are better suited for determination of the directions, basically, of celestial points, of stars, of quasars, of black holes, supernovas, you name it. Okay. And we talk more about direction here, because the distances are so large, so huge, that say, well, if you look at the sky and you see the moon and you see Venus at the other side, and they look, basically we will define the direction towards these two celestial bodies, but not really the distance. We have the issue of a inertial system. Inertial system would be the one that, well, it either doesn't move or it moves with a constant speed. And you have the ecliptic system. E is the ecliptic, and this is what we would think about a inertial system. And they would be what we could have as the most stable. The ecliptic system is basically it follows the ecliptic. If you disregard the ecliptic, we have a system that is probably the most important system that that we can have in geodesy, which is the mean right ascension system at a particular epoch tau 0. This is a reference epoch, and we call this the conventional celestial reference system. Okay, and it is basically determined through astronomical measurements. The main technique used for that is VLBI, very long baseline interferometry. It is a fascinating field, which is again, the CCRS is a basis for what we are going to do, and the whole issue for us is how to establish a relationship between these CCRS with this guy here, that is a system that we're going to be using in practice. It's called the conventional terrestrial reference system. Okay, we need to have the interrelation between those two. The other celestial systems are the mean right ascension system at the date or epoch tau. Tau means date, and date basically means the epoch of the observation. And we have to see here that what connects these two is precession. And if we now take into account notation, we have the so-called true right ascension system. Now, all these celestial systems, they are defined as heliocentric, which means their origin is at the barycenter of the solar system, which is very near the center of mass of the Sun. But in geodesy, they are treated as geocentric because our origin, it will be the center of mass of the Earth. Okay, when we do that, there is no relation, no difference between this guy here, the true right ascension system, and the system of apparent places. Okay, now which means that they coincide. If we keep going along all these coordinate systems, the system of apparent places, then it's very important because it connects the terrestrial systems, the ones with the rectangle, with the one here with the diamond, which is the orbital system, orbital coordinate system that is used to represent the orbits of satellites. And now the whole thing here, that they're all by definition geocentric. Okay, actually not all these ones here, they're geocentric. So anyway, we have then the instantaneous terrestrial system. Okay, this system here is good for the studies of the length of day, and it has to do with the rotation of the Earth. This instantaneous terrestrial system is good for the study of the polar wobble. Okay, how much the pole, the instantaneous spin axis varies. Conventional terrestrial system, this is the one that we have to really understand, because this is the pope of the coordinate systems, and there is a huge relationship with the geodetic coordinate systems, the ones that we use in practice. And here we have the transformation parameters. We talked about transformation parameters before. We're going to use transformation parameters to relate the conventional terrestrial and the geodetic. Now we have the topocentric systems. Topocentric means the observations. The origin is at the topos. Topos means the observation point. So that is the topography, or on the Earth's surface. Local astronomical system, which is very important. We're going to see why, and the local geodetic system. Now there is a connection for the mapping coordinate systems through the geodetic coordinate system. Okay, so Anyway, it is a little bit overwhelming now because we are talking about this for the first time, but you're going to see that this diagram is very, very useful. Okay, so I think I'm going to stop here because probably the file is going to be too large. So, to do this, I have to go here. Oh my God, what is that? How do we get out of here? Desktop. Okay. Okay. And show. These card annotations. Let's see. I go here. Cam Studio, it's open source, so it doesn't matter if I'm looking at propaganda about that. And sorry, there is a background noise. I don't know how to get rid of it.